Okay, so find y prime. So we take the derivative of each term individually. So what is the derivative of 2y cubed? 6y squared y prime plus, what would the derivative of this second term be? 8x minus,
Wait, what's the little thing you have to show? Maybe the d over d of x and the bracket.
alright, so we're taking the derivative with respect to x. And so then that's 8x, and then what would the y become?
1 or negative 1 multiple.
And then x squared is just 2x. So now we want to get y prime by itself. So anything that's not a y prime, we're going to get on one side. And we know 2x minus 8x is negative 6x. I can also factor out a y prime, which would be 6y squared minus 1. Now, divide by the 6y squared minus 1. So y prime equals negative 6x over 6y squared minus 1. And that was actually number 4 from the homework. Because I know you all did your homework over the weekend. So just, wanted to make sure we go over that one.
I didn't know we had.
It wasn't
I didn't
required.
write it down.
It's okay. I might have snuck it in there last minute. I don't remember. Did I tell you I was going to post it, or I just posted it? Oh, Chris is like, yeah, you told us.
We had our cues, that's all.
That was Wednesday. We had a whole class after that.
I'm not there with
It's okay. It was probably that concussion.
it.
I think it's cold in here. All right, so let's look at this one. Find the derivative with respect to x for 7y squared plus sine 3x equals 12 minus y to the 4th. So, looking here, what is 7y squared going to become? 14y y prime plus, now, sine of 3x, that becomes, it becomes cosine of 3x times the derivative of the inside function, which is 3,
Oh, we have to use
chain rule. Yes, because there's a product inside. And then equals, the 12 becomes a 0. Y to the 4th becomes 4y cubed y prime. So now we want to get our y primes on one side. So I'm going to subtract my y prime term. That's negative 4y cubed y prime minus 14y y prime. And this next step's optional if you want to show it, but I do like to factor out the y prime just think it makes it easier to see what we're doing. And then we can divide by the negative 4y cubed minus 14y. And so 3 cosine 3x over negative 4y cubed minus 14y equals y prime. Now, this is perfectly fine. I do want to just show you, if you want to reduce the number of negatives you have, you could just change all of the signs and have a negative 3 cosine 3x. Then your denominator would be 4y cubed plus 14y. But this is fine, and most people would stop here. But this is another option. They are completely the same, completely equal. Okay, I just want to show that. Okay, so let's look at, say we want to find the derivative for e to the x minus cosine, nope, just kidding, minus sine, let's do sine, minus sine y equals x. All right, so the derivative of the exponential is itself. Now, e of x is just e to the x. Now, if it had been e to the 3x, you would have to do the chain rule. Or, yeah, e to the x plus 2. Or if it was something else in the exponent. So now the derivative of sine is cosine, and it's just cosine y prime. It didn't have anything inside. There wasn't a composition, so we didn't have to, yeah, just 1, right. So, and then x, the derivative of x is 1. So now you want to solve for y prime. So we get the y prime by itself. So I'm going to subtract e to the x. That's negative cosine y times y prime equals 1 minus e to the x. So we want to divide by negative cosine y. So y prime equals 1 minus e to the x over negative cosine y. Just another possibility of how you might want to write that. You would write that as, you might change the signs to make that cosine positive. So you would have e to the x minus 1 over positive cosine y. Also, I'm pretty sure, before I say this, I do want to make sure I'm saying this right. Yeah, so you could, this is fine, but 1 over cosine y is the same as secant. Like 1 over cosine is the same as secant. So you also could write it like this. And I don't remember for sure, but did I give you guys like a trig cheat sheet? So, yeah, anytime we're working with trig, I would probably pull that out just so that you kind of have, so yeah, so like here, 1 over cosine is secant. More so too, because if you ever see something, like if you were to ever have 1 over tangent, you might could then rewrite that in a way to take its derivative easier. Like 1 over tangent, like if you had something over tangent, you might would have to apply the quotient rule. However, if you then rewrote it as with the cotangent, it might would be easier. Might not, but I would always pull this out. I forget it was so much, but just something to remember that you have. I might add our derivative rules to that cheat sheet one day. All right, let's look at one where you're going to have to apply some product rules. So this was number 7 from the homework. So we're going to first find the derivative for 4x squared y to the 7th minus 2x equals x to the 5th plus 4y cubed. So what I said a minute ago was we're going to have some product rule here. So if you see here, you see we're going to have the product rule. So if we start with the 4x squared y to the 7th, I don't know if you would want to kind of do the derivative to the side first, or if you want to do it all within. But if you remember from the product rule, the 4x squared, what would the derivative, if I'm looking at the 4x squared, become?
Yeah.
So that would be 8x times y to the 7th plus the 7y to the 6th y prime times 4x squared, which is 8xy to the 7th plus 28 x squared y to the 6th y prime. So now I'm going to go put that over here. And again, you don't have to do this little side work like I do. That's just how it works for me. It works for me. Now the derivative of 2x is 2 equals the derivative of x to the 5th is 5x to the 4th, and then plus 4y cubed becomes 12y squared y prime. I guess I don't really need the brackets. And now we want to solve for y prime. So we have to get y prime on one side. I am going to subtract the 8xy to the 7th and then subtract the 12y squared y prime. So that becomes 28 x squared y to the 6th y prime minus 12y squared y prime. Oh, and I guess I should add the 2. Equals 5x to the 4th minus 8x y to the 7th plus 2. Now factor out the y prime. And then lastly, divide by that binomial. Okay. So that becomes y prime equals 5x to the 4th minus 8xy to the 7th plus 2 divided by 28x squared y to the 6th minus 12y squared. Yeah. I was going to say you could divide out of 2, but you can't because of the 5. Another way, I'm not going to write this, but another way you would end up getting an answer here, depending on how you solved it, you could have ended up with a negative 5x to the 4th plus 8xy to the 7th minus 2, and then on the bottom, the 28 would have been negative and the 12 would have been a plus. So you see, I solved and got my y prime on the left, but if you had solved to get your y prime on the right, then all your signs would be different. But just keep in mind, like, that's equivalent. If all your signs are changed, then they are the same. Okay. So, how are y'all feeling with the implicit differentiation? Like having to use the, when you take the derivative with the y, you put the y prime. Pretty good. It's really just like one extra step, and only for the y's. The biggest thing is I feel like it's easy to forget when you're just like rolling through them, to forget the y prime, and then it gets a little sticky. Or when you're doing things like the chain rule, focusing on, well, I didn't actually take the derivative of the y yet. So in that first part of the chain, not the chain rule, the product rule. So even with the chain rule too, but with the product rule, making sure you only put the y prime when you're actually taking the derivative of that y term. Okay, so now what I want us to look at is I want us to talk about higher order derivatives. So what that means, higher order derivatives, is when you take the second or third or the fourth derivative. And I know the first thing some of you probably are thinking of is, why would we ever want to do that? So when we take the first derivative, what does the first derivative tell us? Slope of the tangent line. Also, when we take the derivative, we can determine where parts of our function are increasing and decreasing. So when we take the second derivative, what that's doing is that's looking at how the graph opens. What I mean by that is it what's the is the concavity? Is it concave up, concave down? For it, like, with concave up, we talk about, like, when you have it like this, your cup, that's convex, and then we have concave, and I think about, like, with concave, if you had like rain, it would roll down, but for convex, when you have like a cup of water or rain, it would pull into the bottom. And so using the second derivative, it tells us, we're able to find those inflection points of where the concavity changes. So, because if you think about, if you have something like this, we have a part where it's concave, but then you also have a part where it's convex. So the second derivative tells us, well, where is that inflection point where the concavity switches? Whereas the first derivative tells us where our graph switches from increasing to decreasing. So just, if I'm thinking about this, I'm just sketching this. My first derivative would tell me my first derivative is going to be able to tell me where does it switch from increasing to decreasing, right? And then again, from decreasing to increasing. Those are the critical values that the first derivative tells us. The second derivative is going to be, now today we're just going to focus on finding that second derivative, and we might even do third derivatives and such, but later this week we're going to look at the application of it, so I just want to get it in your heads. Now what the second derivative is going to do is tell us, well, where do we switch from concave to convex? And so you see that's not the same as the critical value, because your concavity starts to switch at a different point, the how it curves. Okay, so that's why we find the second derivative, not just because I want you to have to do more work. There's an actual reason. So I'll type that. So higher order derivatives. So the first derivative allows us to determine where the function is increasing and decreasing. The second derivative allows us to determine where the function is where the concavity changes, inflection points. Okay, so that's just some notes. Now I want us to actually start with a function. So if we're given f of x equals 5x cubed minus 3x squared plus 10x minus 5. So we're given this. Okay? Determine the derivative of f of x. So the first derivative would be 15x squared minus 9x plus 10. We've done that, right? Yeah? Yep, I do. Thanks. Minus 6x. Now, to find the second derivative, all you have to do is find the derivative of the first derivative. And this is the notation. We use two of the little, what? Apostrophes, yep. Not tilde.
That's okay, you're not
I am not.
the
All right. So the second derivative would be 30x minus 6. Now, the third derivative is just, before we do this, let's show that this is just the derivative of the first derivative. So now this is the derivative of the second derivative, which then would just be 30. So now what if I wanted to find the fourth derivative? And they just change it to a little 4. I don't know why. Probably because if we just keep putting, like, it become a little extra. But that would be the derivative of the third derivative, and what's the derivative of 30? 0. And it would kind of be silly to keep taking derivatives, because what would they be? 0. Anything after the fourth derivative in this case is 0. Okay? So, what you might notice here is what was the highest degree in our original function? 3. So, any degree after that is going to give you 0, because that's the highest you can take before you get to your derivative 0. So we can kind of write a fact. Let's say if p of x is a polynomial of degree n, then p to the k x equals 0 for a k greater than or equal to n plus 1, which is what I just said. Or you could even say for a k greater than n, because I guess technically, I'm not going to get into that. We're just going to do this. We'll stick to this. I'm not going to get too wordy. All right, so if I have 2x to the 5th, then that means the 6th derivative is where we would get a 0 for our derivative. Also, for notation purposes, let's put parentheses around this 4, because we don't want to get this confused as an exponent. Okay, so anytime that we're not using the little apostrophes, which we call primes, let's put parentheses. Now, I do encourage you anything up to 3 to just use the primes, because then I feel like cut and dry. It's never going to it won't get too confusing. All right, so let's find the first 4 derivatives for each of the following examples. So I'm going to write this so that I don't have to keep writing the directions. So we'll do 4 examples. Okay, so let's look at f of x equals 3x squared plus 8x to the 1/2 plus e to the x. Okay? So, first derivative. First of all, when do you think the derivative is, what derivative do you think we're going to get 0? For,
We never get 0 because we need 8.
yeah. For these, yeah, just kidding. Ignore me. If this was a regular function, we would. So, like if we were looking at,
To the 1/2.
yeah, well, if we had it like this, but you're right, we're not.
There's the x too.
Yeah, and the e to the x, because that's never going to go away. So, we're actually going to have to do 4 of these. Sorry, guys. 3x squared becomes 6x plus 8x to the 1/2 becomes 4x to the minus 1/2, and e to the x is e to the x. So, the second derivative, I guess I could have asked you, at what point will our 3x squared become 0? Which derivative will that be? The third. That's how I should have asked that. So now 6x, the derivative is 6. Now for the 4x to the negative 1/2, that derivative becomes negative 2x to the negative 3/2 plus e to the x. Now, the third derivative, that 6 does now become a 0, and we just don't have to write it. So, now what happens to this when we take the derivative? It's going to become a positive 3x to the negative 5/2 plus e to the x. And then the fourth derivative would become negative 15/2 x to the negative 7/2 plus e to the x. So don't let the e to the x make you nervous. I know we don't work with it a lot, or we haven't worked with it a lot, but the derivative is actually the easiest part. So, and you really could keep going, but we're not. So let's look at the second example. If f of x is cosine x. So if that is, what is the derivative of cosine? Negative sine. All right, so now the second derivative. So what is the derivative of negative sine? Negative cosine. Okay, the third derivative. The derivative of cosine is negative sine, so the derivative of negative cosine is sine. And so then the fourth derivative, the derivative of sine is cosine. And then at this point, it would continue in that same, we're back to what we started with. So you should be able to be like, okay, the fifth derivative here is going to be negative sine, the sixth derivative, the seventh derivative, the eighth, the ninth, we're not, you get it. So let's look at another one. Did I say we were going to do 4 examples? Oh, I just said the first 4. Okay, anyway. I did say 4. All right, we'll do 4. Let's do, you know me and f of x. Well, I change it. All right, let's do sine 3x. No, we're not doing any implicit differentiation with this. Not today. That would get really crazy. All right. Sine of 3x plus e to the negative 2x plus let's do a natural log. Okay, we don't do that a lot. So let's do one. So we want to look at the first derivative. So if I'm looking at the first derivative, what am I going to have to do with that sine of 3x? The chain rule. So that is going to be 3 cosine 3x. Okay? Then we're also going to have to use the chain rule with e to the negative 2x. So it's going to be e to the negative 2x. That part stays. And then the derivative of the negative 2x is a minus 2. Okay? Then for the natural log, I'm going to do that to the side. It's going to be 1 over x, but I want to show that. So the derivative of natural log is 1 over whatever was in parentheses. In this case, it's 7x. But you have to apply the chain rule, and the derivative of 7x is 7, which becomes 1 over x. Okay? Or you could even write that x to the negative 1, and that actually will be helpful when we take the second derivative, but because I already wrote it like this, I'm going to leave it. So, now, looking at 3 cosine 3x, you're going to apply the chain rule here. So, cosine becomes negative sine, and the derivative of 3x is times the 3 that was already in the front, becomes negative 9 sine 3x. Now, looking at this 2e to the negative 2x, I know that e to the negative 2x part stays the same, but what's the derivative of negative 2x? It's negative 2, so negative 2 times the negative 2 becomes a positive 4. And then this is an x to the negative 1. This really is. So if I take the derivative of x to the negative 1, that becomes negative x to the negative 2. Okay, so now applying the chain rule here, the derivative of sine is cosine, and applying the chain rule, the derivative of 3x is 3 times the negative 9 is negative 27 cosine 3x. Then, looking at this, we're going to apply the chain rule again. E to the negative 2x, the derivative is negative 2 times positive 4, and that gives us a negative 8 e to the negative 2x. And we just take the derivative regularly, no chain rule or anything. So that would become plus 2x to the negative 3. And then we are just going to do one last derivative. Why am I? Where do I put the little 4? The little 4. So the derivative of cosine is negative sign, so that's going to take away the negative sign that's there. And we're going to say 27 times the 3 is 54 sine of 3x. Am I wrong?
Well, isn't 25 plus 25 50? So that, it's 30.
Oh, it's 3. I was thinking 2. I'm sorry. I was thinking 2. No, but I promise you that I can multiply. But not, obviously not today.
I mean, no one multiply that isn't really like.
At least 27 times 2 is 54, which is what I was thinking in my head. At least I had that part correct. So now e to the negative 2x, and then negative 2 times negative 8 is positive 16. I am correct on that one. And then this becomes negative 6x to the negative 4. Okay? So I said we would do 4, so we can do one more. So I don't look like I don't tell the truth.
Yeah, then we might have to write that on your review.
You might. You might.
About how many problems.
I'm kind of nervous about this. Okay, so f of x equals, I'm going to make this up. X x to the 6 plus 2x to the 4th minus 3x squared plus 8. This is easy because I feel like the last one was not. So, the first derivative, that would become 6x to the 5th plus 8x cubed minus 6x plus 0. Now, the second derivative, that would become 30x to the 4th. 8 times 3 is 24. X squared minus 6. Then we have the third derivative. 30 times 4, 120x cubed plus 48x. And then the fourth derivative would become 360 x squared plus 48. What derivative would I have to take to get 0? We'd have to take it to the 7th derivative, yes.